All right, last video of this lesson is all about error. So what we want to do, remember the whole purpose of a neural net or machine learning is to be able to use errors so the computer can fix itself. So that's the idea. But before I can use the error, I need to know how to calculate the error for these networks. So the idea here is you can kind of see is to use the weights to determine how much air is coming from a particular node. So in other words, like the final layer is pretty straightforward. We know, here, let me use another color. Let me use red. We know the error of the final layer. That's pretty, yeah. So I kind of wrote that in here, right? It's too easy. It's just E1, right? So because that's the node 1, is simply equal to T1 minus OF. Remember, forward propagation gives us EOF. That's the model. That's what your model's currently predicting. That's the target. That's what we'd like to hit. So just subtract those two to get what the error is. And that's simple enough. Now, the the thing that we're going to use is just proportional. So I'm just going to use a proportional argument and say, well, if this weight is 3 and that weight's 1, that means that 3 times of the error that's associated with the final layer gets back propagated into this hidden layer. So for whatever the error sits in this node, then if I'm going to propagate this back towards the hidden layer, then I'm going to say 3 out of 3 plus 1 is 4. So 3/4 of the error comes from this node, this previous node, and then only 1/4 of the error comes from this one. Summon these two, to one or whatever. But just understand that that's sort of the argument. So 1/4 of the error. And so if I'm trying to accumulate all the error in a node, well, I just got to add up all of the errors. We're about to do it right now. So let's just say, change this. We'll say E1 is equal to T1 minus OF1. And then you could keep going. However many nodes you had here in the final layer, you would be using, all the targets and all the actual things that came out from the model, and you'd be trying to, or at least you would be able to know how much error is in each one of those. So the question, oh yeah, this is sort of the hidden layer area becomes more convoluted. How much of E1 comes from the hidden layer versus node 2, assuming proportional. Okay, so you guys get this. So let me just write it out. It's just EH1, right? So the error that's in hidden layer 1 is simply equal to 3/4 of EF, the error that's in, I guess I should have, let me do that. Let me change that. That needs to be EF1. So EF1, and then EH2 is 1/4 of EF1. All right, there we go. Okay. If that's the case, then back propagation of error. What happens when I have two nodes? So that's the point. That's the next little piece here. Um, Obviously, the final layer is easy, and so we'll just go ahead and calculate the final layer. We know that EF1 is simply equal to T1 minus OF1, and then EF2 is equal to the target minus what comes out in the model. So that's pretty straightforward. All right, what I want to do next is I want to calculate how much error is in this node based on the amount of error that was in these two, because this node is contributing to not only this guy but also that one. So we want to sum up those guys. We want to sum up those errors. So what we'll do is we'll start with node 1. So let me just write that. Let me see a good color that I haven't used. I know you guys are probably getting tired of all my colors. Let's try purple. So we're going to call this final 1. And so final 1, how much of this error goes back to the hidden layer, these two hidden layers, basically, right? Because those are the two that's coming into here. So we should have W11 divided by, right, because W11 and W21 are the two numbers that are coming in here, right? So just like we added up 1 and 3 up here to get 4, I'm adding up W11 and W21. So W11 plus W21. So that's the proportion, and then I multiply by the amount of error that's in the EF1, right? So if I multiply that this proportion by the error, then we get that. And so that's what's coming from. So for this final layer node, some of that error is getting proportioned back to node 1 right now, right? So that's this first piece. And then the next one, the blue line here, we're going to say is W. So again, that's 2, 1 divided by the same denominator, right? Because it's 2, 1 plus 1, 1. Again, proportion out the total error that's in EF1, and that'll be also EF1. Okay, so what we've done right now so far is I've attributed some of the error that was of this EF1 error. We've attributed some of it to hidden, attributed some of it to hidden layer 2 based on the weights of these two. And that's what we'd agreed to do above. So now what I'll do is, let's do it in green. I'll call it, I'm going to add the final 2. So let's figure out how much error gets added from this piece. So again, come to node 2, look back, I got W12. So for node 1, which is what we're talking about, we're here. For node 1, I got W12 plus W22. So W12 is in the numerator, and then W12 plus W22 is in the denominator. It's horrible. 2 2's in the denominator, and all of that multiplied by EF2. Again, EF2 is the amount of error in here, but we're attributing a proportion of that back to hidden layer 1, and that's what we have here, that 1 2 over W22. All right, and then the part that's attributed to node 2, right? So because we're talking about that down here, is W22 divided by, let's see, W22 plus W12. And then all multiplied by the amount of error that's in there, so EF2. Okay, so technically, this would be what we would try to proportion back, right? So technically, this would be our error term for the hidden layer. Assuming that proportions do exactly what we want them to do, but we're going to let the calculations be a little bit easier on us. And so let's go ahead and so if I was just calculating EF, the vector EF, of course, that's very simple to do. It's just T1, OF1, and T2 minus OF2. So that's too easy. And we're going to call this EF1 and EF2. Okay. But let's make the calculations for EH a little bit easier. And let's see what I mean by that. So if I were to take out these normalizing constants is what so normalizing constants is what we call them. If I take normalizing constants out, let's check out what happens. So I'm going to let EH, the vector EH, be, let's see, W11 times EF1 plus W12 times EF2, 2,1 times EF1 plus W22 EF2. Okay. Now, how can we make our calculation? I think I've said this a couple times now. How do we make this easier? Well, let's just turn it into a matrix vector operation. It just becomes W11, W12, W21, W22, all times EF1 and EF2. Okay, so this, it actually ends up being the WHF, right? So this would end up being, so the The matrix in between these these two nodes is called WHF. So this would actually be the WHF matrix times EF vector. Actually, I think I can use the capital letter here. Hold on. EH vector. So I would just multiply. So in order to back propagate the error, if you take away those normalizing constants and you just focus on the weights, then you can just simply take the WHF matrix and multiply it by EH. Okay, we're going to do that. That's going to be how we're going to tackle this problem. Otherwise, it would just get too cumbersome by the way the number of calculations that we do every single step. So we need something like matrix multiplication that's going to make our life a lot easier because the computer can do that very, very easy. All right, that's all I got for this one. Again, we're going to cover this in class as well. Make sure you come with any questions that you have about like kind of the ideas, and then we're going to get to coding this sucker up. If you go to your Jupyter notebook, I believe it talks about this as well, and it sort of tries to explain it in there too. So just, again, check it out and use some of the code that's in there. All right, I'll see you next class.